Welcome back, everyone. So now we're going to get to the meat and potatoes. In case you found the previous content a little bit light on the math side, I hope I can redeem myself now. Because now, instead of focusing on the conceptual aspects, I would actually like to do some math. So I've selected two methods that I would like to discuss in further detail. And the first one are wave packet approaches. After that, I'm going to do bulk quantization. So let's start with the wave packet approach. So the ideas are much more broad than doing semiclassics for wave packets. The underlying ideas are perfectly suited to derive, for example, the Hartree-Fock equation or so, because both the ideas and conceptual ideas as well as the mathematics is almost identical. So since you might not be familiar with this, let me first give you some important references. So my most important reference is Christian Lubich's book. In particular, chapters 2 and 5. And some of the concepts are further explained in one of my favorite books of all times, and that is what I call the Bible of Classical Mechanics by Marston and Radziu. In particular, chapters 2.2, 2.4, and 5.4. So this is just to leave you enough breadcrumbs to read further in case you're interested. I mean, especially Lubich's book is very approachable and the ideas are very clearly presented. As usual, we will focus on the non-periodic problem first. And even though the ideas are clearly much more general, I would like you to think of the Schrödinger equation where, for example, the Hamiltonian is the one that we discussed in starting from the chapter about the Ehrenfest theorem. As usual, I will assume that the initial time is 0. That's just a notational simplification since our system is time independent. And in case you need some intuition, I would like you to think about just the usual case of semiclassics on RD, where the Hamiltonian is just minus Laplace plus V of epsilon x hat, where epsilon is our semi-classical parameter. The idea now is very, very simple. And you can immediately tell that the idea is not specific to semiclassics, but it's much, much broader. And the idea is that we approximate exact solutions so this is just psi epsilon of t. We approximate those on a suitable smooth manifold and this manifold is assumed to be a subset of our Hilbert space. And now we can almost immediately translate this to rigorous mathematics, right? So, of course, we are working on the assumption that the initial state lies on M. So this state phi is assumed to be an element of M. So we can now already, our heads, our brain matter gets going already with ideas what this means. And one simple way to express this is as follows. What we are doing is we are looking for the element of best approximation. So that's a trajectory on M that depends on epsilon. Which satisfies the following simple equation. So if we compute the distance between the true solution and our approximation manifold, then the assumption is, and of course, by definition, this is just the infimum over all phi in M. And then you have to take the infimum of the norm difference, of the norm of the difference between the true solution and this vector phi. And the hope is, so this is, let's say, this is a requirement. That's what the exclamation mark means. It just means that the element of best approximation minimizes this distance. And just to emphasize, we're working in the Hilbert space norm here. So the idea is very, very simple, and you see that this need not have anything to do with semiclassics. Semiclassics is just one particular case where we choose the approximation manifold accordingly. Another thing that also becomes clear is that the smooth manifold, because it is a subset of the Hilbert space, can be visualized rather easily. And furthermore, in practical applications, so in particular when it comes to semiclassics, we're given a natural parametrization, a natural choice of coordinates that allows us to connect the this solution here, so we can write it in terms of coordinates. So let's assume that elements on M are parametrized by position and a momentum, let's say. Then this here can be translated to the level of position and momenta. And hopefully these positions and momenta satisfy some simple semiclassical equations. That's the idea. That's it. But of course, you can use other approximation manifolds. As I said, the Hartree-Fock equations can be obtained by choosing, so this is for multi-particle systems, by choosing determinantal states. And you can then also do the same trick here. So this is already quite simple, but I promise that I'll be a little bit more mathematical. So let me write down some assumptions on the approximation manifold. So first, of course, the manifold should be smooth. The first thing is that for all phi in M, the tangent space is a complex subspace of H. So we want to do, at least we initially start with quantum mechanics, and quantum mechanics is defined on complex Hilbert spaces. So not surprisingly, we need to require that the tangent spaces are all complex subspaces. The next thing is, strictly speaking, not necessary, can be removed, but for semiclassics, I think at least is a necessity, namely that the manifold should be finite dimensional. And the third thing is, and this is, it's optional, but we may assume it for reasons that I will explain below. So we may already assume that it consists of normalized wave functions. That just means that phi in M implies that the norm of phi is 1. So the reason why we may assume this is that it turns out we can replace condition C with another one, namely that if phi is contained in M, we can multiply phi by a positive constant, and then it should still be in M. So that M should contain rays of wave functions. And then you can show that with the methods that we're discussing below, that the Hilbert space norm is a conserved quantity. And that means that if you initially start with a normalized wave function, also the element of best approximation will remain normalized. And this condition that M contains rays is just so that you can make sure that these normalized waves are always contained. So instead, I will just assume that M is consists of normalized wave functions. So let's get started. If we talk about the element of best approximation, it seems quite logical to start with a geometric picture. So what we will do here is we will take an illustration that I've just taken from Ludwig's book, because there's no way I would be able to draw something so beautiful by hand. So the first approach uses orthogonal projections. And I will explain this using the illustration, which I've, like a TV chef, I've prepared in advance. So let me just see how far I can push this. Okay, that's probably as far as it goes. So here, this curved background, that's the approximation manifold. This here is the tangent space. Of course, this is just an illustration to make it a little bit easier to see what is going on. And what you can do is you can rewrite the Schrödinger equation . This is equivalent to, well, I can just put the I epsilon on the other side, and I end up with dt psi epsilon of t equals to 1 over I epsilon h epsilon psi epsilon of t. So this psi epsilon corresponds to this. This here is part of this here is a tangent vector. So you can split this into a vector that is tangent to the approximation manifold. So this here would be the time derivative of psi epsilon. This can be split into an in-plane component. This is the component that is parallel to T phi m. And this here is the remainder. And if you know your way around the element of best approximation, the length of the difference is just the length of this vector here. So this here is the true solution, well, the quote-unquote tangent vector, the time derivative to the true solution. This here is the this is tangent to the element of best approximation, and this here is the difference vector, and its length should be small or minimized. How do you do this? Well, these two vectors, so the in-plane vector and the difference, they should be orthogonal to one another. How do you do this? Well, okay, you just use a projection, right? So what I will first do is, so this is an orthogonal projection. And orthogonal projections in a Hilbert space. So remember, one of the assumptions was that all tangent spaces are complex complex subspaces. So there's a one-to-one correspondence to orthogonal projections. Also, they're assumed to be finite dimensional, so we don't have to worry about taking closures and the like. And well, what is the how are these projections defined? They are simply the projections onto the tangent space at phi. So now we know that the element of best approximation is characterized by the tangency condition. So let us start, for example, at time 0 for conceptual simplicity. So we start, by assumption, we start our Schrödinger equation at phi. So this must be an element of the tangent space of M at phi. And okay, if we compare this with the true time derivative, which is the right-hand side here, then what we get is well, we can replace the second guy by the right-hand side of the rewritten Schrödinger equation. And And this now makes complete sense. And by definition, this difference must be this vector here. All right. So, but of course, so the important point is that in general, maybe I should copy this picture over so that I have it at the ready in case I need it again. So of course the point is that in general the time derivative of the true solution at any time, in particular time equals to 0, is not an element of the tangent space, right? I mean, this is what we would expect. Otherwise, the approximation would be exact. So this here is the generic situation. And I could write down already the solution in terms of the projectors, but it is helpful to rewrite the condition in multiple ways and then discuss them separately. So the first point is that, okay, let's just write out the different equivalent conditions. And for simplicity, I will work at time 0. But that readily generalizes to all the other cases. So in accordance to the picture, what I would like is that the difference between my tangent vector and the true time derivative that comes from the Schrödinger equation. This should be, so as a reminder, as a visual reminder, this is this guy here. This has to be perpendicular to the tangent space. So this has to be perpendicular to T phi of m. Okay, and now we can reformulate this condition as follows. Well, we can just write it out. So this just means that for all phi in T phi m, the scalar product between phi and this difference has to be equal to 0, right? I mean, this is just this condition here written out. And okay, this is equivalent to so this equivalence is really just a consequence of the Pythagorean theorem. And that is that this is equivalent to finding a phi epsilon from the tangent space so that the distance, and this was the initial picture, the initial claim, that this is an element of best approximation. So that this distance is minimized and another way of writing this is using projections. And this is the, let's say, the theme that I started out with, right? Because you can just say, okay, I can simply rewrite the element of best approximation for this subspace here using the projection. So what is phi epsilon? We can explicitly write it out. Phi epsilon, the tangent vector, that is equal to the orthogonal projection. So we are, the base point is phi. That's why I have to plug in phi times 1 over I epsilon h epsilon times phi. All right, so that's more or less it, right? So, and of course, the important thing is that, sorry about that, that these arguments extend to t different from 0. So overall, let's summarize. The formal solution to this minimization problem is as follows. We can just take this equation here and translate it forward in time. And then the element of best approximation satisfies the following self-consistent equation. So the tangent vector is equal to, well, the projection onto the base point at phi epsilon of t times 1 over I epsilon h epsilon applied to phi of epsilon t. And with this equation, it also becomes obvious why, or how rather, our problem may become nonlinear, right? Because the dependence of p on the base point need not be linear, right? So you could here, this is the source of the nonlinearity. So if the manifold M is nonlinear, So if it's not a linear subspace of your Hilbert space, in which case this approximation problem would be much, much simpler, then, well, the tangent space depends on the choice of base point. And then in all likelihood, the equation, unless, some miracle cancellations occur, in general, what you will end up with is a nonlinear equation. So is this satisfactory? Not really. And that is because, formally I've solved the problem, right? I mean, if I'm just a mathematician not so much interested in solving real world problems, I can say, okay, that's it. So this is the equation that the element of best approximation shall satisfy. But then you might ask, okay, can you compute it? Can you in some particular cases? And then, maybe they will have to shrug. And the source of the issue is that this here is a self-consistent equation. So don't get me wrong, we've made some progress, but we're still some ways off when it comes to solving the actual problem. So, but let me just put a nice box around it, because that's one of the important equations. All right, so I think this is good enough for first part. Let us continue with a second point of view next.